Okay, so a few odds and ends, picking up from last time. So we had, I was having trouble with authentication in terms of this table of these primitive types that's in the Adler book that's on the syllabus. So I didn't totally solve that, but I have a workaround. And so this is this table. It's only showing the first two lines at the moment, but it's basically categorizing into different categories what these fundamental primitive types are. And it says there's integer, there's double within the vector group. And then assuming that I can go down a little bit, integer, double, complex, characterological, raw, and then it talks about these compound objects like lists and pair lists and some of these things you may not have heard of. So the basic idea is when you do type of, you're going to see one of these kinds of descriptions of what the type of the object is. And if you do class, then what the class tells you is basically that classes are objects that are types of objects that are kinds of objects that are built on top of these primitive types. So they're sort of higher level entities. So when, for example, when we did, when I asked what the type of was of that column that was a factor variable, a categorical variable, we got that integer. You'll notice there's no factor in here. So what that's indicating is that factors are basically built on top of integer vectors. They're still vectors. But they have this additional information about what the levels are and what the mapping is between the number that's associated with the level of the factor and the actual string that's associated with being the label of the factor. And then as when we start to talk about object-oriented programming and different kinds of objects in the more formal object-oriented context in R, what we'll see is that all the S3 objects are basically built on top of lists. So any S3 object is basically a list with some additional stuff associated with it. Okay, so any questions about that? Yeah, questions?
Is there an equivalent table that does the subcategories?
The subcategories
Or like
of...
the ones that build them off the list?
Well, not really, because as a user, we can develop new kinds of S3 and S4 objects. Yeah, so that list is basically as large as we want it to be. I mean, there are some that, and any given package in R will have its own set of different kinds of objects. So if we look at the stats package, which is a built-in package that obviously does statistical stuff, there's an LM class and a GLM class, and it's sort of up to the developer who writes additional code to say what the additional kinds of objects are. Other questions? Okay, so let's go back to where we left off, and I left you guys with a little puzzle to think about between Monday and today of what's going on when I said if we wanted to take the pieces of a list and R-bind them together, the way that we would do that is with do.call, because R-bind in and of itself is expecting the dot argument, which is basically just it's expecting any arbitrary number of like objects separated by commas that it's going to then R-bind together. So a list is not in that format. A list is just a single entity. So it doesn't like it, in some sense, it doesn't like it if we just do R-bind with a list. So I said this is some nice functionality that will do what we want it to do. But then I asked the question, well, what happens when we actually do an R-bind of either one or more lists? And so here was an example where I had my list being a list that contains 3 vectors, and then I have my list 2 being a list that just contains as one element a character string, and then I R-binded it together. So what were people able to tell from either from this example or from as you were thinking about things over the last couple of days about what's going on here?
So the mega is over here is the 2x3 matrix, and each element is a list.
Okay, so it looks like maybe each piece of this is a list. So what do we know about matrices? Christian?
To contain the same.
Okay, so we know any element of the matrix has to be the same kind of object as any other element of the matrix. So in this case, it looks like R is treating a list as being. It looks like it's able to handle having a matrix of lists, and in the sense that each list is considered to be equivalent to another list, and they can get glommed together as in the form of a matrix, right? So there are a couple more questions that we could sort of address as we look at this. what's happening? Why are there 3 ZZZs here?
It's copying it so that it has the same dimensions as the list.
Okay, so the first thing, and we're going to get back to why there are 3 pieces here, but the first thing that's already getting R binded together is initially is this list, which has 3 pieces to it. So ZZZ only has 1 piece to it, so it has to do some sort of recycling. You guys should have all seen recycling in other contexts, and this is just it coming up in the same context here of it's trying to combine together rows, but one of them has 3 things, another has 1 thing, so either it needs to give us back an error, or it needs to somehow fill in the remaining pieces. Okay, so that's what's going on there. Presumably each of these elements is, excuse me, is a list. So let's actually just look at that. I'm going to do a little trick called last.value that's going to recover what I last printed to the screen, or what was last evaluated. So now I can say temp. I can say what's the dimension of temp. I can say what's the class of temp of any of the elements of temp. Say the second 2.2 element says it is indeed a list. Okay, and if we actually look at temp 2.2, oops, or temp 2.3 for that matter, we can see it's a list in another way by seeing that it's got this little double bracket notation that indicates we're looking at a list, and then it shows us what the pieces of the list are. So I think the last question that one might ask here is, I mean, maybe there are others, but the last one that occurs to me is why is it that when it does this R binding, it considers there to be, if I look at this original list here, I could think of that as just being 1 thing, or if I look at it, well, okay, there are 3 pieces of the list, so I could think of it as being 3 things. And obviously from the result we got that it was interpreting that first list as 3 pieces instead of as 1 piece. So the question is, why did it not try and make a 1-column matrix of lists? Why is it making a 3-column matrix of lists?
List is also wheeled as a vector.
Okay, so you're young? Okay. So a list is also a vector. So when rbind gets an input that's coming to it, rbind, what is rbind trying to do? Well, in the more familiar context that when we think about rbind, we give it a set of vectors. It tries to rbind them together, usually into a numeric matrix. So it's looking for a vector, and then a comma, and then another vector that it can just start pasting all together. When it gets in a list, lists in R are actually also considered to be vectors, and we can see that with is.vector of my list. Should say true. Says true. So it thinks of the vector as a list with 3 elements in it. So then when it's doing the R bind, it says, oh, the first thing you gave me is 3. The rest of the things I expect to have 3 pieces to them as well. Okay. Any questions or comments about that?
What happens if you have like a list of 2 and then a list of 3? Would that give you an error?
I'm not sure. Let's try it out. So we've got, I can probably equivalently do it as 1 and 3, right? So I'll just do it with my list 2 and then my list. Is that still going to address your question, you think?
Well, no, because if you have 1, then it can be...
Ah, right, okay. So let's make a new guy. My list 3 is a list of 7, 3. Okay, so now we want to do rbind of that. Okay, so some of you have probably seen, in fact many of you may have seen this idea of recycling, that if the number of things you're trying to match up are not divisible by each other, it's going to do the recycling but give you a warning that that's going on. So it says this thing about not being a multiple in vector length as the first argument. So it does the 7, 3, tries to match that together 3 things, starts to recycle, but it can't really completely recycle in the sense of matching things up in a clean way. So it does that, but tells you that gives you a warning. Okay, other questions? All right, let me go back and figure out where I am. Okay, so we're still sort of skipping through a bunch of the initial elements of this unit. When we get to section 5, which should happen shortly, we're going to stop and be much more focused. But for now, I'm still sort of skipping through and hitting a few highlights of things. I want to comment a little more about coercion in the context of factors, which I also mentioned in the boot camp, so this will be repetitious for a number of you. But I think it's useful to highlight again. So suppose I set up a vector, a factor vector. So the idea here is I'm setting up a vector of sort of student achievement on some categorical ordinal scale of basic, advanced, proficient, and minimal, or something like that. So each student gets a score, and then each student gets a categorical level of achievement, and then I'm gonna try and now associate the categorical level with an actual numeric value. So I want to be able to do some mapping and association between these different kinds of information about the achievement. So now I'm going to say, okay, I'm going to assign basic to be a number score of 1, minimal 3, advanced 13, and proficient 7. So all well and good. And now if I want to feed in advanced and pull out the score associated with advanced, well, of course, I should get a 13 now if I'm just doing this lookup by name. So that indeed happens. So I might think that I can do the following. I want to take the third student. That third student is advanced. And I want to look up the associated numerical score for that student. So if I do that, that doesn't look so good, right? So I did this in the boot camp. So a number of you have sort of already seen this. But if we think about what's going on here, what kind of input is the square bracket operator expecting? Even not from a formal sense. If you were writing a language and you're deciding how the square bracket operator works, what would you expect? What would you want it to have as an input? Gotcha.
An index.
Okay, so we might have it be an index, namely a number, right? Or we've already seen we can give it a character string advanced. But actually, what we're giving it when we pass in students of 3 is we're actually giving it a factor, right? So if it's not natively set up to handle a factor, what's going to happen? It's going to have to do some sort of coercion or casting of the variable into the kind. Either it's going to have to give us back an error, or it's going to have to convert the input to something that it can work with. So it must be behind the scenes converting it to something. So implicitly, when we do this, we're expecting to or hoping that it will convert it into the character string. Right? Why do you think it doesn't? And this just goes back to the start of class of what we've already talked about.
Factors stored as an
Okay, so the factor stored as an integer, so the natural thing, if you sort of think about it from the perspective of how R was written, is it's not going to convert it to a character string, it's going to convert it to an integer. That integer then goes in as the index, but the problem is that the ordering of the factors is not necessarily the meaningful ordering that you would expect unless it's an ordered factor. And so it just gets converted essentially to some arbitrary number between 1 and 4. I guess there are 4 different kinds of there's basic, proficient, advanced, and minimal. And so it happens to be that advanced happens to be the it looks like it's not the sort of index that we expect it to be. So if I do as dot integer of students of 3, it says 1. Okay, so score of 1 is indeed minimal, which has a value 3 associated with it. Okay. So sometimes when we're working with a language, particularly one we're not familiar with, or even sometimes with ones we are familiar with, they do unexpected things, but this is a computer, right? It doesn't, in general, it shouldn't be doing random sorts of things. There's a logic that's internal to how the language is written, and it's following a set of rules. And part of our job in terms of understanding what's going on is to understand what those rules are and why things happen in the way that they do, so that we don't get tripped up by it. So if we actually wanted to do this and carry out the operation that I sort of set up as the toy problem here, I would actually have to formally convert it to a character string, then pass it into the single bracket operator. Yeah.
By default, is factor ordering
That's a good question. I would expect it might be, but I'm not totally sure. Okay, so moving on again, we're skipping around a bit. I'll just point out quickly that I don't want to go into a lot of detail on this, but when we do apply, if we use an apply, we can do an apply to arrays, to higher dimensional matrices, basically. So we don't just, we can do an apply where we apply things to rows or columns of a matrix. We can also do apply where we do an apply applied to subsets of a higher dimensional array. So these are just some examples here of taking an array and, say, applying the min along the second and third dimensions here. And do I have another one up here? It's x. Oh, I guess that's the only one I have. But you can basically give it whatever dimensions you want to do the operation on in terms of doing the subsetting. Okay, there's a little section here on linear algebra. That's 4.4. We're going to have a whole unit and like 5 days of class on linear algebra later on in the semester. So I think I'm not going to say anything about that now, but do look over that on your own just to have a little bit of background on that in case any of that comes up over the next few weeks before we get to the linear algebra. So I think what I want to really spend time focusing on in this unit is functions and frames and environments associated with functions, and then strings and regular expressions. So I'm going to skip to section 5, and we're going to go through this in quite a bit of detail. So are there any questions from any of the stuff that I skipped over or any of the earlier parts of this unit before I launch into this in detail? Okay. So basically any operation in R is a function. Even when you use an operator like plus or the double square brackets or the single square brackets or things like this, all we're basically doing in the guts of R is basically evaluating a function with some arguments. And that's sort of hidden in some cases in terms of the operators and sometimes in terms of, even in terms of doing assignment. When I say x gets 3, I could have actually written that as the assignment operator with the arguments x and 3. Let me do it with the arguments x and 5 to show that this actually does do that. It's actually just carrying out a function operation. Okay, so basically anything you do in R is evaluating a function on a set of arguments. So if we think about functions, we can sort of think about them generically in the big picture as we have some body of code that we need to evaluate that's going to do the things that we want to do. And we need to have a context in which that code is going to operate. We need to know what the objects are on which that code operates and what the values of those objects are. So you can think of evaluating a function as basically having a body of code and then setting up what's called a frame that holds the objects on which the code is going to evaluate. And then the R interpreter is basically marching through the lines of code and doing things with those objects. So in general, most of those objects that things are being done with in the context of the body of the function of the body of the code of the function, most of those objects are going to be in that frame of the function. But sometimes R will come across names of objects that are not sitting in that frame, and it needs to have some rules of where to go look for those objects. Either it needs to error out and say, I can't find that, I'm stuck, or it needs to have some rules of where else it might go look for those objects. And the idea of this unit is to try and get a detailed understanding of some of those various operations that I just sort of gave an overview of. So the way that R does this, it has its own set of rules for doing this. This is similar to and both similar to and different from the way that other languages will do this. And so part of the goal of going through R in detail is to get you guys really proficient with R, but another goal is just to bring up some of these issues that come up in programming, and then if you go off and learn another language, you'll see some parallels to some of the concepts, or you'll see parallels to the concepts that we discuss here, but implemented potentially in somewhat different ways. Okay, so the other part of our goal here is, as we think about functions, is when we're writing our own code, one of the goals of writing good, clean code in R is to write functions that do specific tasks and do specific tasks well and are modular in the sense that ideally we'd like to have a lot of relatively small functions, each of which does a particular task well, and then to do a larger task we combine those functions. And the idea is that that's going to keep your code cleaner and it's going to be easier to debug, because if you have a small function, you sort of know what it does, you can do a really careful job of checking that it handles everything really well, and then you can just use that function and be confident in your use of that function. The other thing is if you have a function that does some specific task really well, then you don't need to keep rewriting that function. If I write a big function to handle some task I want to do, and then I write another big function, I'm going to end up rewriting pieces of things that are common to those separate tasks. So the idea is whenever you start to do that, to try and write that actually as a function. The other couple other principles in writing our own functions, but also in terms of functions that are built into R, is that in general, one of the principles with R, but not necessarily with other languages, is that the result of the result of running a function is basically just whatever is given back as the output, and there aren't any side effects that affect your global working environment apart from that. We'll talk about that more in a bit. And the other is that in general, we'd like to have functions be self-contained, so in general we'd like to have them only operate on the inputs and produce the outputs, and not take information like from global variables that are outside the function and pull those in. Because if you're writing a function and you want it to be really robust, you don't necessarily know what the values of those objects are outside of the function. So if you're relying on doing something on the data frame named x, and x is not a data frame that was passed into your function, the value of x sitting out in the global environment could change at any point arbitrarily. Okay, so let's start by thinking about what are the possible inputs to an R function. So basically, you can pass arguments to R either in order. So if we look at the ln function, we can either give it first a formula and then data, then potentially some subset argument and these various other things. And we don't have to name the first argument's formula. We can just give it, and R is just going to match by position. But we can give things out of order by giving it basically a key value pair. So I could do something like I could do lm of y tilde x, and then I could give it some data frame named cars, and it will go ahead and proceed happily ahead, just matching these two to those first two items there. But I could also say lm of data equals cars, formula equals, and it will be perfectly happy with that. As you can see here, R will take default arguments. So if you don't give it, for example, QR, it's going to use a QR decomposition in computing the regression estimates, even if you don't tell it to do that explicitly. You can pass in null as an argument. Either you can do it, or it could be a default here. And that functionality is helpful for situations where, in some cases, you don't want to have additional options, but you may, when you're running this function, want it to be able to do some additional things that wouldn't by default necessarily be done. And then this triple dot argument can get used in a couple different ways. One way it gets used we've already seen with rbind, that if you want to have a function that will operate on an arbitrary number of like inputs, you can often that will come up as you'll have a triple dot, the ellipsis argument as the first argument, and then the function will basically just process through all of those like elements. But we can also have it later on, when it's an argument later on in the set of arguments. The way that's generally being used is that those arguments are basically unspecified arguments that are then going to get passed through to some other function that gets called within the body of this original function. So as an example of that, this is my definition that I used. I put this, for example, in my .r profile file, because I happen to like, when I do a scatter plot, I don't happen to like the open circles or the sizes of those open circles. Those are the defaults in the R plotting function. So I basically create a new function that I call pplot for point plot, and I say there's going to be arguments x and y. I specify the plotting character and the size of the things that are printed out as defaults for my function. And then I say dot, dot, dot. And then all I do is I call the original plot function, I give it x and y, I specify the PCH argument to plot to be what I got as the input here, and similarly for CEX. And then I just pass the rest of these things along. So this pplot operates essentially the same as plot would, but it allows me to override the defaults for PCH and CEX. So that's an example of how the ellipsis gets used. And if you want to know how to manipulate the dot 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 arguments in the way, for example, with rbind, where if it gets a set of like arguments as the first as that ellipsis, you can do things like this. You can refer to the pieces of it as dot dot and then by number, or you can convert it from a list. You can convert it to a list, and then you can work with the elements of that list. And you could query how long the list is to see how many pieces came into your function, et cetera, et cetera. So any questions so far?
Yeah, what
Christian?
happens if, for instance, I use two functions inside a function, but one of these doesn't recognize one of the dot 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 parameters that you give? For instance, in the pp plot, if I have specified, for instance, breaks equal to 1 to 5, and after plot, I have this function, but the plot function doesn't recognize the break character, right? The break argument. So does it make an error or something?
Yeah, I'll answer the question and see if I've answered the question that you're asking. If you pass in an argument to a function that's not expecting that argument, it'll error out.
Yeah, but this argument will be used by another function, for instance, the hist function after that.
So I think I'm not quite following. So you're saying that. So yeah, let's see if we can map that onto this. So you're saying we've got pplot, and then are you passing in breaks here to pplot?
Yeah.
Okay, so you're passing in breaks equals whatever, c of something.
Yeah.
Okay, now what are you doing within pplot?
Yeah, and pplot is defined as having the function plot.
Yep.
And after that, we have a new function is of the data.
Like this?
Yeah. And so if we run it specifying.
And so you're going to pass on the dot 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 to each of them?
Yeah.
I think that will probably work. You could test it out and see, because plot gets. Well, I don't know. I'm not sure. That's a good question. We'd have to try it out and see. That would probably take more time for me to code than I want to spend right now. That's something you can just play with and see. It should work here. The question is if you breaks becomes part of breaks I guess becomes part of the dot 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 and then gets passed into plot, and the question is whether it's going to be a plan. Other questions? Okay, another nice, some occasionally useful thing is that you can actually have arguments. The default values of arguments relate to other arguments that are part of the function. So if we think about the gamma distribution, you can parameterize the gamma distribution either as shape and rate or shape and scale. And the scale and the rate are just inverses of each other. Right? So this is, I sort of hate the fact that the gamma distribution is like this because it causes no end of difficulties. But be that as it may, that's how it is. And so the way that R handles the gamma function is it says the second argument is shape, the third argument is rate, and then the scale argument is set up by default to just be the inverse of the rate. So if you pass in the rate, it'll just calculate the scale as 1 over that, or you could pass in the scale instead. And I think R in its guts is basically working with shape and scale. So I suppose it would be possible to pass in shape, rate, and scale, and have rate and scale be inconsistent with each other. And if you looked into the guts of the function, you should be able to see what it does in that situation. I think what happens is it just ignores the rate in that case. Okay, this is actually a bit out of place, but I think it's a useful example to look at. So we'll talk through it anyway. So when we use apply, if we look at the arguments to apply, it says there's basically an input data argument, a margin, i.e. a row or a column or a dimension of an array that it's going to operate on, or potentially dimensions of an array, and then it's expecting a function. So we're basically able to pass around functions just as any other kinds of objects. Everything in R is a function, and that includes anything in R is an object, and that includes functions as well. So we can pass in functions as arguments. And one thing that comes up when we see this is the function doesn't have to be named. It can be created on the spot. So if we think about the R interpreter going through and working through this code, it says, okay, I'm going to match X to be Matt. I'm going to match margin to be 2. I'm going to match fun to be this. Well, what is this? This is just a bit of R code that can get evaluated and will create a function on the fly. So it's now create a function. That's an object that just gets passed in as the capital FUN argument to the apply function. So then the other thing I wanted to bring up here is the thing that's a bit out of place, which is if we do this, I'm going to create a matrix 1 to 9. Oh, I haven't mentioned this, but a good thing also to mention here is R is column major. So R stores matrices in order by column. So if you basically look at a matrix, it's basically stored as a vector where it's strung out and flattened out by column. So if you looked at this fundamentally in the underlying C object that is storing this, it would be 1, 2, 3, 4, 5, 6, 7, 8. That's like Fortran. It's unlike C. I don't remember how Python handles things. I don't remember how MATLAB handles things. But we're going to see this come up again in the future in terms of thinking about doing numeric calculations. And in terms of, it's going to come up when we think about efficiency as well. Okay, so I fill up this matrix here. By default, it's going to fill it by columns. And now if I do an apply, I can do an apply by each column, and I'm going to take the vector, I'm take the input, which I'm calling back, so that's going to be each column, and I'm going to subtract off the first element of that input. So this should take this column, subtract off a 1 from each of these elements. Then it should take this column, subtract off a 4 from each of these elements, and then it should take this column, subtract off a 7 from each. So indeed, that's what it does. It gives us back 0, 1, 2 in each of the columns. Questions about that before I go on to the trickier part here? Okay, so we could also do this by row. So if instead I do the apply by row, and I think about what should have happened, or in some sense what one might expect is what should have happened. I guess let me just print out Matt again. So if I do this by row, I should get 147. That should become back when I first walk through this apply and operate on the first row. I should subtract off a 1. That becomes 0, 3, 6. Same thing happens there. This becomes 0, 3, 6, and this becomes 0, 3, 6. But the result is transposed relative to what we might expect, right? We're thinking, okay, this is just going to operate by rows. It should give me back a result that's in the same sort of row column format. So what do you think is what do you think might be going on here? So we can think, again, we can try and think through this and sort of try and think about, well, sort of what are the steps that might be going on in order to produce the result here and see if we can parse our way through what happens. So apply is basically going through row by row, and it's going to it's going to do this function in each row. So it does the function on the first row, and what does it get back? What kind of object does it get back after it operates on that first row? Okay, should give us back a vector because the input was a row, which presumably is a vector. I suppose it could be a one-row matrix, but it is actually a vector, and that's sort of not too surprising. So it gives us back a vector. So so just suppose that we're R, we're sort of holding on to that vector. Now we go through and we do the operation on the second row. Gives us back another vector. Do the third one, it gives back another vector. So we now got 3 vectors sort of sitting there. And now R needs to give us back the result. So it looks like what it's doing is it's pasting it together by column instead of by row. So why does that make sense in some sense, at least in terms of the logic of R here? Okay, it's column major, right? So we just talked about the fact that R by default treats things, matrices as operating basically in terms of columns. And so when it sees vectors that it needs to combine together by default, it's going to combine them together by column. So the result is that this thing is transposed relative to what you would expect. So that's a little bit I mean, it makes sense if you think about the guts of what R is doing, what the rules are that R is built upon. But it's a little bit frustrating because this could this is a bug waiting to happen, right? You write this code, you think, oh, I'm going to operate by row, I'm going to get back a matrix that is in the same order, or whatever, you know what I mean, as what I gave in. But the result in this case, since it's a 3x3 matrix, is still even of the same dimension. So your code can just keep plowing ahead. Numbers keep getting evaluated, stuff still gets done, and presumably at some point you hopefully realize that something went wrong somewhere, but it might be hard to track down. Okay, any questions about that? Yes, and what's your name?
Zoe.
Zoe.
So, are there any ways to fix this problem to make it accurate?
No, I mean, you just end up having to do a transpose. You sort of have to know that this is going to happen and do a transpose. I mean, oftentimes when we do apply, we're going to get back a scalar number instead of getting back an entire vector. So then when we paste together the scalar results, we just get a vector and it doesn't matter. So this doesn't come up all the time, but it does come up every so often. Okay. Let me say one thing about what happens when arguments get passed into R. So basically, R arguments get passed in, and something happens that's called pass by value instead of pass by reference. So basically, if you pass an argument into R and then you manipulate the argument that you passed in, it has no effect outside of that function. So that's called passing by value. Basically, you pass something in, a copy of the thing that you have. So if I do, let me make this a little more explicit. If I do mean of x, it's going to make a copy of this input x, assign that copy basically in the frame of the function, the objects that it manipulates in the context of the body of the function. And any manipulations to that object are not going to affect the original x that's sitting here in my global workspace. So that's called passing by value as opposed to passing by reference. I say that a copy is made, and in some sense it is, but there are contexts in which that's not quite true, and we'll talk about that in a couple weeks. But basically, a copy is made, and anything that gets done to the thing inside the function does not affect things outside of the function. And the reason that the R developers did that was their principle in developing this was they didn't want functions to have side effects and sort of things that happen sort of invisibly to the user that might surprise the user. And so that was the principle that they used. The downside of it is that more copies of objects get made than would be the case if you could manipulate the object inside the function and have it affect the state of the object outside the function. So sometimes if you're working at big objects, that can come back to bite you in terms of having there be more memory being used and more computation involved in having to actually explicitly make the copy. The one exception to this is that if you manipulate graphical parameters using the par function within a function, that affects the graphical parameters outside of the function. So that's just something to be aware of. Okay, let me say a little bit about outputs from a function. This will be pretty quick.
So is there any pass by constant reference in R method?
There are ways to basically pass things around by reference, and we're going to see that in some detail in Unit 6 in a few weeks. Okay, so if we're returning stuff, so the basic mode of a function, you can think of it as a black box. It takes inputs, does something to them, produces an output. We can produce outputs in a few different ways. Basically, if we do return of something, then that's going to return the output that's going to return whatever is inside the return back as the output of the function. If we don't give it a return, it'll by default just return the result of the last statement. And it will actually sort of do this invisibly in the sense that I'll mention via the demo. So here I have a function. There's just one line in the body of the function. So I've sort of written it in shorthand without a lot of indentation and whatnot. So if I evaluate this function, you'll see it doesn't print anything back to the screen. But if I assign the result to A, it should give me back, it should tell me that A is indeed 9. So it's basically returned it invisibly. It hasn't printed it to the screen, but it does allow me to assign it. And I can also get that same behavior with, where am I here? by using the invisible function. So this is basically like return, but it says don't print the result to the screen, but do allow the user to assign the output to a new object. So that's what invisible does. And then just to point out that unlike languages such as MATLAB or I think Python, you can't return multiple outputs. The result of an R function has to be a single object. But the reason that we can get around that easily is because a list can be any arbitrary collection of heterogeneous things. We can always return a collection of things as a list. And that's the standard way that we'll do things. So for example, with a linear model, it's going to return a list, which is actually, it's going to return an object, an LM object, which is built upon a list and is fundamentally a list. And that LM object is going to contain all sorts of heterogeneous information that are results of running a linear regression. Okay, so let's launch into this next question of variable scope. So the basic idea here is suppose I'm a function. Sounds like some Sesame Street. I'm a function. Suppose I'm a function. I'm working through some code, and the code says do something with an object whose name I don't recognize. It's not in the current working. It's not in the current frame, which I'll define more formally in a second. I need to know where to go look for that object. So if you were thinking about developing the language, there are a few options you have for what rules to set up of where to go look for that object. So where are some of the places you could go look for an object that's not in the frame of the function? So suppose I have a function that I am defining, and I say, okay, I have some function of x, f is my function, and I return x times y. What are my options for what to do if when I'm the function, I'm working through this and I see a y? What possible things could be the behavior? Okay, could you give me an error message to say I don't know what y is? Right? Tom, did you have an alternative?
Maybe we'll look for the variables in your workspace, and then maybe it looks for variables that are automatically in the what do you call it? In some of the basic
Packages?
packages. Yeah.
Okay, so it might just go look in your general workspace, which is called the global environment. So that would be like that would basically be if you look for a global variable, which comes up in other programming language contexts. So that's certainly a possibility. It might also want to go look in other packages that have gotten loaded into R. So the idea is that the objects that get loaded in a package are kept in a separate environment or workspace from the objects that you've created on the fly when you're working at the console, for example. So those are another couple options. What if I instead said, let me just go to the demo code because that's already drawn out here. Okay, so this is basically another way of stating this example, which is that suppose I define x in the global environment, I then have a function that says do something with x, but there is no argument x here. So it could just by default go look in the global environment. So that's one possibility. So that would be one kind of behavior that we could postulate. It gets more complicated if we think about the following. Here I'm going to define, this is not very well indented. Oops. Okay, here I'm going to define a function within a function. So I'm going to define my function f. Within that, another function f2 gets defined, and then I call that function f2. So if I'm in f2 and I'm looking for x, what are my options for where to go look for x? I could directly go to the global environment, right? But I could also go look for x within the context of the function f. Right? So that would be another option for how I could set up these rules. Okay, so the basic way that R decided to set this up is something that goes by this sort of again, what word am I looking for? Maybe overly formal name of lexical scoping. Go back to the PDF here. So basically what happens is, now let me actually define these words that I've been throwing around, but not really defining formally, of environments and frames. So basically, the frame of a function is the collection of objects that are associated with that particular function. And that is also an environment, because what happens when R sets up the frame is it basically also sets up a pointer to, or sort of a reference to, what's called an enclosing environment. And the enclosing environment is the next place that R goes to look for objects that are not defined in the current frame of the function. So an environment is basically a collection of these objects, which is a frame, plus this pointer to where to go look next for objects. And the sort of trick with R is that the enclosing environment for the environment or frame of a function is not the function from which it was called. It's the place in which the function was actually originally defined. So that's the trick that the trick that we need to be aware of here. So we can start to work through these examples and see this actually in action and make sense of what's happening. So let's go back to R. So I'm going to set up a variable x in my own workspace in the global environment, and then I'm going to have this function x that uses an x, this function f that uses an x, and we need to see if it actually does what I said it will do. Oh, right, I don't want to pass in x because this function is not expecting an argument. That's part of the point. Okay, so if I run this function f, it is actually going to take the square of 9, take the square of 3 and produce 9. So it goes to look for x, and it finds x here. This is actually, the global environment is the first place it looks for this x, and the reason it's the first place it looks for it is that f is defined here in the global environment. So the enclosing environment of the frame of f is the global environment, because f is defined in the global environment. It's just defined here, in this case, at the console at the command line. So it first goes to look, if it can't find x in the frame of the function as one of the arguments or as part of the code of the function, it then goes to look in the global environment. And and you'll also note here that I modified x within the function. And if I now print out x here, it's still 3. So this is this pass by reference versus pass by value. The fact that I changed x in the function had no effect on the x outside in the global environment. There are ways to actually modify the value of x outside of the function. One of them is to do something like this with a sign. And here I'm saying assign to the name x, in quotes, the value x squared within the environment of the global environment. So that will actually change the x outside, but I had to do it explicitly here. Okay, so here's my next example. I still have x being, or I'm going to reset x to 3. And now, if I look at this, f2 is defined within f. F is defined in the global environment. So now we've got a set of enclosing environments. I have the frame for f2. That environment is enclosed by the frame for environment for f, and that's enclosed by the one for the global environment. So if I am looking for x here, it should first look in f. It doesn't see any x's in the frame of f. So then it's going to go back further up and look in the global environment. So this should basically print out right, so now if I call f, this should indeed print out 3. Okay, so we're basically running out of time. So what I'd like you to do for Friday is take a few minutes and just look through the rest of the examples in this section 5.3 of the notes. Look through those, think through those, and that'll set us up to just work through those on Friday. And I've just posted problem set 2 in GitHub. It's going to be due 2 weeks from Friday. And most of the problems are set up, and once we work through this stuff on functions, you'll be able to do the first 3 of the 4 problems. And the 4th problem has to do with a lot of regular expressions that we won't get till next week. And that problem is not quite, I haven't quite finished writing out the problem, so You can look at it to get a sense for it, but you probably don't want to quite start on it.
Where's it?